Hi everybody, here is your video for section 3.1.1, which is all about, well, first off, chapter 3 is all about justifications and similarities. So I want to start off by apologizing that this video is so late. It's been a crazy weekend, as you guys all understand, so bear with me on that. But chapter 3 is all about justification and similarity. So before we even talk about any of that, I have a little joke for you guys. So what did 0 say to 8? Nice bow. Alrighty, so in this chapter, so not just a section, but in the chapter, you will learn how to support mathematical statements using flowcharts and conditional statements. Remember, you learned what a conditional statement was last chapter. You will learn about the special relationships between shapes that are similar or congruent. And then you will learn about how to determine if triangles are similar or congruent. So in section 1.3, you organize shapes into groups based on their sizes. So we are going to be looking at different figures and going back to that chapter in that section a lot during this chapter. And then today you will specifically be introduced to a new transformation that enlarges a figure while maintaining its shape. So it's called a dilation. So we're making it bigger, but it's keeping its shape. So it's creating a new enlarged figure. So what I'm going to do here is I'm going to show you guys a video. Let me go to the section that I did in class today. I videotaped myself in my room, and it's going to be 3.1, so it's called the warm-up stretch. So you guys are going to watch a video of me doing the warm-up stretch, and then when you guys come into class, you only have 3.2 and 3.3 to cover, as well as the exit ticket, which will cover some stuff later. So that is what you are going to watch right now, is going to be 3.1. Alrighty guys, so this is what I'm about to show you is actually the warm-up activity for the first section of the new chapter, chapter 3. So what we are going to be focusing in today is dilations. So dilations is actually a form of translations. It's changing a shape, you're keeping it the same, but we're changing it. So this chapter is all about dilations and similarities. So we're going to be comparing shapes, using shapes in different ways. To look at this stuff. So here is a nice little star, and what I have taped to the board here are 2 rubber bands stuck together. So what I'm going to do is I'm going to show you what it looks like with 2 rubber bands, and then I'm going to show you what it looks like with 3 rubber bands. So the idea here is that I'm going to take the 2 rubber bands, and I am going to keep this knot right on my star at all times. So I'm going to move it around so that way my knot is always on my star. And we're going to see what figure it draws. Alright. So the first one is with 2 rubber bands. Okay. So I'm going to start here, and I'm not even going to look at my marker. I'm just going to draw it out. And I'll pull the camera closer so you guys can see it once I'm done drawing it. Alrighty, so as you can see, the star got a little bit bigger. So you guys can see the setup here of the rubber band. So I used 2 of them there. I kept the connection of the rubber bands, so the knot where the 2 rubber bands connect on the black star, and then I was able to draw my blue star. So I'm actually going to do that again. Just this time I'm going to have 3 rubber bands. So I'm going to connect another rubber band here. And take like 2 seconds to make a prediction. Do you guys think it's going to get smaller? Do you think it's going to stay the same? What do you think is going to happen here? So take a couple seconds. Alrighty, and then let's do it. So this one's going to be in red. So same idea. I'm going to keep my first knot on my black star at all times. Alrighty. So I'm sorry it's hard to see, there's a little bit of a glare, but there you can see it's getting bigger. So this is exactly what happens when we do a dilation. So a dilation is when we're actually multiplying the numbers by something. So if you were dilating it, let's say from black to red, we were dilating it by 4. You'd be multiplying everything by 4. It'd be getting 4 times bigger. If we were dilating the black to the blue by 2, we would say we're doubling the size, or we're making it twice as big. So that's kind of what we want to think about when we're doing dilations, is you're making it bigger, you're doubling it, you're tripling it, you're making it 4 times as big as what we have right there. So that is the first section of the chapter. So that's 3-1 right there for you guys. So you guys can actually skip that question when you guys come in, and you guys can jump right to 3.2. Alrighty, so hopefully you guys liked that video and found it interesting. So the more rubber bands that we added to the link, the bigger the image got. Even though the first rubber band was only being stretched to the first star, the other rubber band, or the other 2 rubber bands was what made it stretch out and expand. So you can actually do that with any figure you want. It doesn't have to be a star. It could be tons of different things. So that's basically what a dilation is. Now I'm going to take you guys over to the methods and meaning box. So this just writes down or describes more of what a dilation is. So a dilation is a transformation that maintains the shape of a figure by multiplying its dimensions by a chosen factor. So you can double it, you can triple it, you can multiply it by 4. So in a dilation, a shape is stretched proportionally from a particular point called a point of dilation, or a stretch point. So if you refer back to that video, that stretch point would have been where that rubber band was taped to the board. For example, in the diagram at the right, triangle ABC is dilated from triangle A prime, B prime, C prime. Notice that while the dilation changes the size and location of the original figure, it does not rotate or reflect the image. So the idea is that your shape is staying the same, everything's staying the same, it's just getting bigger. So you're multiplying it by something. All right, and then the last little part here is going to be this review preview problem. So the only review preview problem where you're going to go over today is 3-9. You'll have 3-5, 6, and 8 to do for your exit ticket. And remember that if you aren't getting your exit tickets done in class, it's super important that you're revisiting them and finishing them for your homework quizzes and your tests, because that stuff's going to appear. And that you guys are writing down these examples into your notes, because like I said, it's going to come back. Okay, the stuff that we go over is obviously you're going to revisit it. So for this question, it says examine each diagram below and justify the error in each diagram. So for the first triangle, we're given all of the side lengths of the triangles. Not a right triangle, so we can't use the Pythagorean theorem, but we can use the idea of side lengths here. So remember our rule, the 2 smaller side lengths, the sum of those cannot be bigger or cannot be smaller than the longest length. So 9 has to be smaller than 5 and 3 added together. It cannot be 5 and 3 added together either. Remember, it would create a straight line. So for this one, the error is going to be triangle inequality. Because 3 plus 5, which equals 8, is less than 9, which we cannot have. Big no-no. Alrighty. The next one has a nice square here, which means we're probably going to the Pythagorean theorem. So we need to see if the Pythagorean theorem holds up. So remember, the Pythagorean theorem is a squared plus b squared plus c, or equals c squared, which you guys should all be a pro at by now because of your guys' videos. So we want to see, does 5 squared plus 12 squared equal 14 squared? So we have 25 plus 144, and that's going to get us 169. And I'm just going to go ahead and do 14 squared is going to get us 196. So those guys do not hold up. So that one would be the Pythagorean theorem. Is not holding up. Alrighty. I apologize. I don't know why this one's labeled 1 and 2, but whatever. For 2, based on these side lengths, we should be saying that this is what type of triangle? They have two sides that are similar, which means this should be an isosceles triangle. Hopefully that's what you guys say. So in an isosceles triangle, remember this side is equal to this side, which means this angle has to equal this angle. So that's all I'm going to test out here is I'm going to do 65 plus 55, and that's going to get me 120, and then I'm going to take 180, and I am going to subtract 120 from it, and that gets me 60 degrees. So I know that there is no way, based on the fact that those side lengths are equal, that's an isosceles triangle because the angles do not line up here. So the base angles are not equal for that guy. So no way, it cannot work. So that's our mistake for that guy. Alrighty. So you guys will come in, like I said, and do question 3.2 and 3.3. And I will be around to check that. No learning log like always. Make sure you guys are writing down the notes for dilation and the definition. And then you guys will have your exit ticket to do at the end of class. So if you guys have any questions, please let me know. Other than that, I hope you guys have a great night, and thank you for being so understanding that this video was posted so late. I really appreciate it. Have a great night.